Yay!
Yay! Hey everyone, this time we're starting a new unit on energy, and I'm not really going to lecture much about what energy is, or indeed try to even define it, because there really isn't a good definition. I mean, not when we're trying to learn things at this level. Instead, what I've found is that the best way to learn about energy is to learn what it does, just to look at some examples. Because energy is really, when you get down to it, it's a description of a system, right? It's not a thing. You can't, see it. It's a description of a system, and it turns out that it has this great property that it's conserved. That's physics talk for doesn't change. The total amount of it doesn't change. And so learning how to compute the amount of it in a system turns out to be really important. So let's just look at an example. Let's see how this works. One aspect of energy that we're going to be calculating is called work. And just like in the colloquially everyday use of the term work, if you lift a bunch of weights or move things around, you say, man, I've done a lot of work. And in some sense, that's right. Work is, here's something I've done. I've asked a bunch of juniors and seniors, undergraduates, tell me what the definition of work is. And what they tell me is, what they tell me is work is force times distance. And that's kind of right. It really is. I mean, it is fundamentally, it's a force times a distance, but we have to be really careful. So yeah, if you apply a force to moving something across a carpet over some distance, you have done, in physics terms, you've done work. But let's be just a teeny bit more careful. It is force times distance, but watch this. Let's do this little example, and we'll expand on this as we go along. Let's say I'm moving something from this R initial to R final, right? So I want to move something from this point to that point. No problem. And I think what I've got is, let's say R initial, where does it start? It starts at like -3 and -2 meters. And R final, where it ends up, is like 3 and 4 meters, right? That's my vector notation, 3i plus 4j. Okay, so Ri to Rf, that vector is the displacement, right? That's the path that it goes from the beginning to the end. One thing we're going to want to know is, what is the displacement? This is way back at the beginning of the course of study. So delta R is final minus initial, right? So if I subtract those two vectors, here's what I get. What would that be? 3 minus a minus 3, 6. 4 minus a minus 2, 6. Okay, so my delta R, this thing, is the vector 6, 6. That kind of makes sense, right? I might have even drawn it right. It looks like it's 6 to the right and 6 up from where it started, so that looks about right. Okay, so let's suppose that this is sort of a rail. This object has to go along this track. It's constrained to be on this rail or something. So let's suppose that there's a force, and this force is acting in a slightly different direction. Let's say the force is acting like that. So maybe I got a force that is like acting 2 in the x and 1 in the y newtons. Maybe it's something like that. All right. If this is the case, here's what I'm interested in. I can figure out, this concept of work allows me to figure out how fast is it moving at the final position, right? After this force has been acting on it the whole time. So let's think about it. Is there a component of the force that's acting along the direction of motion? Well, sure. Here, maybe we'll do it in green or something, right? This is the amount of force along the direction of motion, along that track. So that amount of force is doing some pushing, right? There's some acceleration there. So the speed is going to be changing. That's what acceleration means. Our speed's going to change. For example, what would happen if the force, let me just draw one and then I'll erase it. What would happen if the force was like that? If the force is like this, if it was perpendicular to the direction of motion, then there's no component of the force that's acting along the direction of motion, so no bit of that force is going to be pushing this thing along, speeding it up or slowing it down, right? It could be going, force could be backwards, it could be slowing the thing down. So if it's perpendicular, if the force is perpendicular to the direction that the thing is moving, then it's not doing any good. It's not speeding it up or slowing it down. No component of the force is helping. So let's get rid of that. It's disappearing slowly, sort of like the guy in the looper. There we go. All right. So saying that the work done is force times distance, we have to be careful. If the force is perpendicular to r, there's no work done. It's not increasing the speed at all. So what matters is the amount of force along the direction that the thing is going. And how do we figure that out? We already have a tool to do it. How do I know how much force is going in that direction? It's the dot product, right? So here we go. The work done is just going to be the dot product of F dot displacement, because that picks off the amount of F that's going in the direction of r. Notice what we get is just a scalar, a number. It's not a vector. The dot product just gives us a number, right? And this number is going to be in energy units, joules, at the end. Okay, so first of all, let's figure this out, and then we'll see how that affects things. So the work done, how much work do you do? It's F dot delta R. Okay, well, that's going to be pretty easy to do, because the work done is 2, 1, dot. What's my delta R? Like 6, 6, right? And how do you do the dot product? You multiply the x's together, then you multiply the y's together, and then you add them up. So 12 plus 6, 18 joules. Okay, so what we've done is we've added 18 joules of energy to this object from beginning to end. Suppose it starts from rest. That's going to be the easiest thing to start off with. So at the beginning, this thing wasn't moving at r initial, and then at the end we've added 18 joules of energy to it. All right, so what good is that? What that does is this must be, according to the work energy theorem that you've probably seen in like your book, this is equal to the change of kinetic energy. In other words, this is the final minus the initial kinetic energy. Well, the initial, we're starting off at rest, right? So that's going to be 0. If it was already moving, you would just compute the initial kinetic energy. Okay, and what is kinetic energy? So 18 has to be, what is kinetic energy? It is 1/2 mv squared. Cool. And let's go ahead, I'll just call that final, right? The initial was 0, so whatever. And so now we can figure out what V final is. So V final is, oh, I have to tell you M. I don't know, suppose M is, did I do this ahead of time? M is 200 grams. Cool. So my V final is 2 times 18. It's going to be the square root of 2 times 18 over 200 grams is 0.2. Everything always in kilograms, meters, seconds. And if you do this, 36 to square root of 180, right? So that turns out to be like 13.4. Very nice. That's what I get at the end. So what's neat is just knowing the amount of work done, the scalar product of force and displacement, I can figure out what the final speed is. Because what's the effect? What's the effect of dumping a bunch of energy into the system of this particle is that I speed it up, right? There's some component of force along that direction. So I'm speeding it up. How much did I speed it up? 13.4 meters per second. Neat. All right. So if you hear people say work is force times distance, again, look, that's kind of right. But you have to be careful. It's the amount of force in the direction of the distance. That's what matters. And so we actually have to do the dot product if they're not going in the same direction. And also, that's only if the force is constant. If the force isn't constant, then we have another problem. So we'll deal with that when we get to it.